Hello everybody, this is Dr. Christopher White and welcome back for part 3 of the Precambrian and its life history, focusing on the Hadean and the Archean. Now before we go any further, let's just get the code word for this presentation out of the way. The code word for this presentation is zircon. I repeat, zircon. That's Z-I-R-C-O-N. One more time, that is zircon. So please make sure you write that down, put it somewhere safe because you're going to need it later. So in the end of the last lecture, we'd been discussing greenstone belts. So we'd been looking at how greenstone belts represent probably pieces of oceanic crust that have been deformed and metamorphosed. And so these greenstone belts consist of sequences of mafic and ultramafic volcanics, so metamorphosed basalts and komatiites, and on top of that we have a sequence of very silica-rich metamorphic rocks which probably represent the sediments that were on top of these mafic and ultramafic volcanics. So the presence of these ultramafic volcanic komatiites shows that the magmas that were being erupted at the time that the seafloor was being formed could have been anywhere up to 1,600 degrees Celsius in temperatures. These are very, very hot magmas, or should I say lavas. In contrast, the maximum temperature of a modern basalt, so a basalt is pretty much the hottest lava that gets erupted onto the surface of the Earth in the modern environment, is going to be about 1,200 to 1,400 degrees Celsius. So there's been a noticeable decrease in the temperature of lavas that are being extruded onto the surface of the Earth since the Archean. So the question is as well, why did we have all these very, very hot lavas in the Archean? Well, we've already discussed the reason for it. It's because the Earth's interior was a lot hotter. So because the Earth's interior had all of this additional heat of accretion and these higher concentrations of radioactive isotopes, it meant that the mantle could have been anywhere up to 300 degrees Celsius higher in temperature than its present value. So at these higher temperatures, we can start to melt the ultramafic rocks of the mantle a little bit more easily. This means that we can melt not only the more calcium-rich minerals that would normally give us a mafic lava, but we can also melt the more iron and magnesium-rich minerals like olivine and pyroxene. And because we melt the olivine and the pyroxene, we actually get a magma that's very, very rich in iron, magnesium, and some calcium. And so this is an ultramafic lava. And the other thing is these ultramafic lavas would have been produced in quite large volumes, and the volume would have been large enough to have allowed the magma to make it from the mantle all the way to the Earth's surface. Now the thing is unfortunately, because the mantle has cooled down, what happens now is yes, we do still form these ultramafic magmas in the mantle. They will rise, but because we're forming them in much smaller volumes, as they're working their way through the crust, they cool down very quickly and they never have a chance to make it to the Earth's surface. So unfortunately, we no longer have these komatiitic lavas, these ultramafic lavas, being erupted, unfortunately, because they would be quite cool if they were still being erupted, but alas, the Earth's mantle has cooled down to the point where we don't really form enough ultramafic magma to allow this to happen anymore. So the sedimentary rocks of our greenstone belt, also now metamorphosed, they dominate the upper portion of the greenstone belt, and they consist mostly of metamorphosed rocks that we interpret as being greywackies, so quite muddy sandstones and also mudstones. Now luckily there are some sedimentary structures that are still preserved in these metamorphosed sedimentary rocks, and in some instances we actually have cross-bedding present, which suggests a unidirectional flow. We can also see in some cases we have normal gradings. That means the bottom of the layer consists of coarser sedimentary clasts and the top of the layer consists of finer sedimentary clasts. There's an upward fining of a layer. So this kind of might sound familiar, because now the first thing to remember is we're dealing with a marine environment, and marine environments aren't really known for unidirectional flows. So a unidirectional flow is something like a river, or the wind only goes in one direction. In the case of the oceans, the forces that we have moving sediments around are waves and tides, and those are bidirectional flows. So the fact we have a unidirectional flow in some of the, well, indicator should I say, of a unidirectional flow in some of these metamorphosed sedimentary rocks means that we have to come up with a method for which, through which we can form these observed textures. And the most obvious one are turbidites. So a turbidite is of course a unidirectional flow. The sediment is sliding down the continental slope and onto the continental rise, so it's only going in one direction, so that helps to explain the cross-bedding. And if you remember, turbidites are also known for their normal grading. Coarsest class at the bottom of the layer, finest class at the top. And so what it looks like we have pieces of deep ocean seafloor which are being covered by these turbidites. So it would seem that greenstone belts probably represent some kind of deep ocean environment from the Archean. Now, that's not always the case. We do also have minor quantities of sandstones, limestones, and sometimes banded iron formations. We'll discuss those in future lectures. And these rocks tend to be more shallow in terms of their depth of formation. And so it would suggest that some greenstone belts formed in shallower water, although the occurrence of sandstones, limestones and banded iron formations is much smaller than the turbidite-related metamorphosed sedimentary rocks. So it would seem that a lot of these greenstone belts are probably representing deeper marine environments, but occasionally we do get some that represent more shallow marine environments. So how do we actually form these greenstone belts? Well, greenstone belts occur in terrains consisting of multiple parallel belts, as we saw in the diagram a few slides ago. Now, each of these greenstone belts is separated from the next greenstone belt by a granite gneiss complex. So the volcanic rocks of the greenstone belt, now metamorphosed, were deposited in a number of different tectonic settings. There's a number of ways that we can form these mafic and ultramafic oceanic rocks. So they could be associated with spreading ridges, like the Mid-Atlantic Ridge. They could be associated with island arcs. They could be associated with something called back arc basins, which we'll discuss more in a couple of slides. They could be related to ocean plateaus. So an ocean plateau is where we have typically a flood basalt eruption onto the seafloor. So very often there's a hot spot trapped under the oceanic crust, and obviously the magma from that hot spot burns its way through the crust and pours out onto the seafloor in large quantities. And what it can do is it can end up forming a raised area of seafloor that has a flat top to it. So it's essentially an oceanic plateau. Or the formation of these mafic and ultramafic lavas could be related to rifting continental margins. There's lots of ways that we can form the kinds of rocks that we see in the oceanic crust, in the greenstone belts. So the question then becomes what are the preferred models for greenstone belt formation? When it comes down to it, there's really only two that tend to, fit most of what we see. So the first model is called the back arc model. So here's our basic situation. We have our island arc here, so our line of volcanoes, and we have a piece of subducting oceanic crust. Now we know a subducting oceanic crust goes down into the mantle, reaches a depth of about 100 to 150 kilometers. It releases water, melts the mantle. That produces a mafic magma that gets stuck at the base of the crust. The heat from that melts the crust, producing a felsic and intermediate magma that then gets erupted at the surface, and we see that as volcanoes. So we're familiar with that model. Now the thing is as part of this process, we can get something called slab rollback. So you can see our piece of oceanic crust is descending down into the mantle. But sometimes the angle of our piece of oceanic crust will change. Sometimes it will steepen, so the piece of oceanic crust will naturally increase its angle, so it will come in at a much steeper angle like so. Now this means that as the oceanic crust falls backwards, it means that the continental crust here naturally has to extend to fill the empty space. And so this can lead to the formation of what's called a back arc basin. And if the back arc basin stretches the crust to the point where it becomes thin enough, we can begin decompression melting of the mantle. We know when we melt the mantle through decompressional melting, we produce a mafic lava. The mafic lava will obviously work its way through the thin crust using faults as a conduit, and it will then erupt itself onto the bottom of this back arc basin. Now the great thing about these back arc basins is they tend to fill with water. So what you have here is you have yourself a very small sea. And so this could help to explain these pillared basalt textures that we're seeing. So these could represent basalts being erupted onto the seafloor of a back arc basin. So that's the lower and middle portion of your greenstone sequence. And then we have high ground here and high ground here that are going to be actively eroded. That's going to contribute sediments that are then going to be deposited over the top of our mafic and ultramafic volcanics. So now we have our complete sequence, don't we? We have our mafic and ultramafic lower and middle layers, and we now have our clastic sedimentary silica-dominated upper layer. And obviously, what needs to happen later on is there needs to be compression, so the area needs to get squished, and then this package of, these package of lavas with the sediment over the top get folded to give us our syncline. Now the nice thing is that this process is going to happen again and again and again in approximately the same location. So we'll form one back arc basin, that will be compressed and closed up, then another one will form, that will be compressed and closed up, then another one will, so we'll get these repeated periods of back arc basin formation. And so this could help to explain why we get these greenstone belts all orientated approximately equal to each other, or probably, let me try that sentence again, all orientated approximately parallel to each other. So it helps explain orientation, and it helps to explain why we get repeated greenstone belts one after another. So let's just have a look at a modern example of this process. So here's our model. So here's our island arc. Here's our piece of oceanic crust, and here's the piece of oceanic crust which is subducting. So what we have is we obviously have our oceanic crust subducts, it melts, produces magma, that magma rises to the surface and feeds the volcanoes. Now, because our piece of oceanic crust is going to start rolling back like so, it's going to start extending this area of the overriding piece of crust. So this area here is going to start being stretched to fill the gap produced as the oceanic crust rolls back. So this means the island arc literally splits clean in two. And so you end up with your volcanic islands here. You have a line of now extinct volcanic islands behind it. And in the middle we have our back arc basin. And this is where the crust can be thinned sufficiently to allow the underlying mantle to melt through decompression. And that will then allow basaltic, or mafic lava should I say, to flood onto the seafloor of our back arc basin. And obviously sediments are going to be provided by the erosion of the volcanic islands, and also sometimes from pyroclastic volcanic deposits. And so if we want to look at a modern example, so here's the Lao Basin, so here's New Zealand down here. So we're going to have, so Australia is going to be off to the side down here, Papua New Guinea is going to be up here. So we have New Caledonia, we have Fiji, and we have Tonga. And you'll see there's the subduction zone right there. You can see it quite easily, that's the trench. But you'll notice we have these lines of islands. So we have one line of islands coming down here, and we have another line of islands coming down here. And so if we zoom in, what can we see? So here we have the Tongan Islands, so this chain of islands right here. And over on this side, we have the Fijian Islands right there. And you can see we have this area of crust in between, and you can see it displays all of these parallel lines running approximately north-south. So these are the faults which are being produced as the crust in this area is getting stretched. Okay, so the crust from here to here is actively being pulled. This half is wanting to go this way. This half is wanting to go that way. And so that means obviously we have a crust that's being extended, it will fracture, so it will fault, and obviously because it's being stretched, the crust will naturally thin. That's allowed the mantle underneath to melt, producing basaltic magma that then floods out into this back arc basin. So this is a modern example of this process. And then later on what will happen is compressive tectonics will squish this area and it will push these two island chains back together. So the Tongan Islands will come this way, the Fijian Islands will come this way, and the sequence of rocks in the middle, our mixture of mafic volcanics and sediments on top, will get compressed and it will form this nice syncline which we see in most greenstone belts. And so the basic model of back arc basin formation for greenstone belts is nice and straightforward, and it works it's quite logical. Now, the one problem is with this model is it's a bit difficult to envisage it being able to produce numerous greenstone belts. So in theory, we could produce a few greenstone belts using this method, but the possibility of us being able to produce, half a dozen to 10 of them in the same location, that's a little bit more tricky. So the mechanism itself makes very good sense, but its ability to produce all of these parallel greenstone belts that are running next to each other, it's a little bit more difficult to explain. Now, in order to explain how we could get multiple parallel greenstone belts next to each other, the second model is called the island arc model. So here's our basic idea. So here's our piece of continental crust over here. And here we have two island arcs. So we have one island arc here and one island arc here. They're obviously separated by a piece of oceanic crust, and that piece of oceanic crust is being subducted. So this piece of oceanic crust being destroyed, and so this island arc here is moving eastwards towards this island arc here. Obviously, in between them, we have a sequence of sediments, marked out here as this kind of light green, and obviously we also have the oceanic crust there as well. So remember, the oceanic crust itself is going to consist of a sequence of basalts and gabbros, and on top of it we're going to have our sediments. Now, the greenstone belts themselves are actually modelled as being the island arcs. Okay, so every time one island arc hits another, so we're going to have this island arc come over here, it's going to hit this one. The sediments in between are going to get compacted to give us this belt right here. Okay, so this is going to be our granite gneiss complex, and our greenstone belts are going to represent the island arcs here and here. Okay, now if we have repeated collisions of island arcs one after another on the same continental margin, we are going to end up with bands that run approximately parallel to each other, aren't we? And this is what we see when we look at the greenstone belts of the Superior Province. We have one belt running approximately parallel to another, so we have greenstone, granite, so we have greenstone, granite gneiss complex, greenstone, granite gneiss complex, greenstone, etc. And so this model actually makes quite good sense. The presence of the sediments here helps to explain the granite gneiss complexes in between the greenstone belts. Brilliant. The fact that we can have multiple island arcs stacking up on the continental margin helps to explain how we end up with all these greenstone belts right next to each other. Also, very, very helpful. The one problem, though, is that when you think about island arcs tend to form from felsic and intermediate volcanic rocks. Greenstone belts, by their nature, form from mafic and ultramafic igneous rocks. So obviously this is a little bit problematic. So the island arc model helps to explain some of the features we see, like these multiple parallel belts which are separated by these granite gneiss complexes, but it does have the problem that the material that we would be forming the greenstone belts from would actually contain a significant amount of felsic and intermediate igneous rocks, which in theory would make your greenstone belt a lot more quartz and feldspar rich than it really is. Now, this is obviously a problem, and some people have said that, right, well, maybe the lower portion of the greenstone belt, so our lower and middle portion, so our mafic and ultramafic rich layers, maybe that represents parts of the oceanic crust, and the upper, more silica-rich layers represent the felsic and intermediate volcanic rocks on top. So that's a possible way of getting around it. But, this model is a little bit tricky in terms of actually trying to explain where the greenstones or the mafic and ultramafic rocks actually come from. So you can see that both of these models have their problems. The first model, the back arc model, helps to explain where the mafic and ultramafic rocks come from. It explains wonderfully where the sediments come from, and it can very easily lead to the formation of a single syncline, very easily. And you may be able to generate a few synclines using the same technique in the same area. However, if you want to produce multiple greenstone belts all orientated approximately parallel to each other, an island arc collision model is actually far more reasonable. And so you can see our problem. We have these two models that kind of work and kind of fail at the same time. And to be honest, you can pretty much argue forever as to which one is more correct. So, my personal preference is I on the whole, prefer the back arc model more, but it doesn't explain everything that we see in greenstone belts, and so it's not a perfect model, so work still needs to be done. But the moral of the story is these greenstone belts exist, they're showing us we have stable seafloor, and they're also clearly demonstrating to us that by the Archean we have fully functioning plate tectonics. So we've discussed that the greenstone belt shows we've got plate tectonics, and the formation of the cratons also shows us that we must have plate tectonics. So during the Archean, like the Hadean, the Earth's lithosphere was probably thinner, so our crust was thinner, it was hotter, and it was more buoyant. At the same time, we also have a mantle that was hotter, and so subduction would actually be quite difficult. So if you think about it, it's quite easy to subduct a piece of oceanic crust down into the mantle if the piece of oceanic crust is very, very cold and dense, and the mantle isn't too hot. Because if the mantle is hot, it naturally wants to rise, and so that's going to resist anything trying to subduct down into it. So in the Archean, when the mantle was a lot warmer than present, it would have naturally wanted to rise, and that would have made it more difficult to have subducted material into the mantle. At the same time, the material that you're trying to subduct is naturally also going to be hotter, and so it too is going to want to rise a little bit, so it's going to be difficult to subduct as well. So we have this problem where during the Archean, subduction will have been a pretty difficult process. Not impossible, just a bit more tricky than it would be in the modern setting. So during the Archean, the continents, which we now describe as cratons, would have grown rapidly through two processes. So we've already discussed the first one, that's continental accretion. So that's when new material gets added to the edge of your continent. And that can be done by island arcs sticking themselves onto the side of your continent through collisions, or it can be due to the deposition of sediment along the edge of your continental landmass. Both of those processes will result in the diameter of your continent increasing. So your continent will get larger. The other process that's going to help to increase the size of our continent is called underplating. And so this is the process of essentially igneous rocks, or should I say magmas, intruding and getting stuck in or under the crust. Now, these magmas will of course eventually cool down, they will crystallize, and they will form rocks of their own, so something like granite, for instance. And so all of this magma getting trapped in the crust or under the crust will actually help to add new volume to your piece of continental crust. So it's not increasing the diameter of your continental crust, but it is going to help to increase the thickness of your continental crust. And so over time, what's going to happen are your continents are naturally going to get bigger, and they're going to get thicker. And so this process which is occurring in the Archean is going to start making these continental landmasses get larger and larger and larger. Now, when it comes to the onset of proper plate tectonics, things get a little bit difficult. Now, in terms of the plate tectonics, we've already discussed how where we have environments like the Ishiwa Greenstone Belt or the Nuvagatuq Greenstone Belts of Canada, we can see we have pieces of what look like oceanic crust. Okay, now the process of taking these pieces of oceanic crust and pushing them out of the oceans is called abduction. Because remember, if our pieces of oceanic crust were not pushed out of the oceans, well, they would have been subducted and destroyed by now. So the very fact we have these pieces of oceanic crust means that they must represent pieces of the oceanic crust that have been pushed out of the ocean basins onto the continental crust. And so this process is called abduction, and the pieces of oceanic crust that get pushed onto the continental crust are termed ophiolites. So an ophiolite is a piece of oceanic crust that's been pushed onto continental crust. So ophiolites become less common after about 1 billion years, but the most important thing are the earliest good examples of ophiolites are the Ishiwa Greenstone Belt in Canada. So we know we definitely have ophiolites 3.8 billion years ago, and we do have some older examples, but they're not quite as good. So you can argue about, do they really represent ophiolites? It's one of these great things about science. You can have a good argument about something. So we can say with certainty that 3.8 billion years ago we have functioning plate tectonics. So the fact that we have functioning plate tectonics obviously gives us the force required to actually push the oceanic crust onto the continents. But most of the time, a piece of oceanic crust will just subduct under a piece of continental crust. So the fact that we have this abduction tells us that subduction is not an easy process during this time frame. Because if it was easy, subduction would happen and the ophiolites wouldn't be forming. But because subduction is a little bit more difficult because the mantle's so hot and the oceanic crust you're trying to subduct is so warm, well, it means it's more difficult to get that oceanic crust to dive down into the mantle. And so abduction is more likely to occur. So the chemistry of the oceanic crust of the Ischior greenstone belt indicates it was produced at a divergent plate boundary. Once again, a good indicator that we have plate tectonics functioning. And of course, the only way to actually form an ophiolite is via abduction, and abduction can only happen at convergent plate boundaries. So we know for a fact that 3.8 billion years ago, we definitely had divergent boundaries, we definitely had convergent boundaries, and we definitely had plate tectonic forces that were moving these pieces of crust around. So we've got that, that's fine. We can't argue with that in the slightest. Now, whether these tectonic processes were similar to modern examples, or whether they represented a more chaotic system with localized divergence and convergence, is uncertain. As we've discussed, the rocks we're dealing with here have had a pretty long and hard life, so they're not in the best condition. So we always have to be very careful about the conclusions that we draw. So that's why we are saying with certainty we definitely have plate tectonics 3.8 billion years ago, but there are some indicators that we may have had abduction occurring before 3.8 billion years, suggesting that the process of plate tectonics may actually be older. So by 2.7 billion years, so that's the late Archean, so heading towards the Proterozoic, it can be agreed that we have fully functioning proper plate tectonics happening. So there were differences compared to modern plate tectonics, the most obvious of which is that during the Archean, sediments weren't being deposited on passive continental margins. So what's a passive continental margin? So a passive continental margin is like the east coast of North America. So it's boring. Sediment gets transported by rivers and it gets deposited onto a nice, stable, dull continental shelf. Nothing exciting going on. No volcanoes, no earthquakes, pretty boring. Now compare that to somewhere like the west coast of South America. That's referred to as an active continental margin. So we have a subduction zone, which means we have volcanoes, mountain buildings, earthquakes, and so we have these two different environments. Now the thing about a passive continental margin is sediments will actively be deposited on it. And we know by now that where we have these marine continental environments, we tend to get a nice sequence of sandstones, mudstones, and if conditions are correct, carbonates as we go into deeper water. So where we have a passive continental margin, we will see rocks which give us this sandstone, mudstone, carbonate sequence, and that tells us this was a passive margin. It was nice and boring and stable. In contrast, we don't have that at active continental margins. At active continental margins, we have lots of deformation, lots of pressure, lots of heat, and so the rocks that are in that area tend to get mucked about with quite badly, so there'll be lots of deformation, for instance. So when we look at the Archean rock record, one of the things that we don't see are large quantities of these passive continental margin sequences. So that would suggest that most continental margins, so most coastlines during the Archean, were active. So you would have had continents almost completely surrounded by subduction zones. So this is obviously very different to the modern scenario where our continents may have a subduction zone on one side and they'll have a nice passive margin on the other. So What we notice is that as we transition from the Archean into the Proterozoic, we begin to see these stable continental margin sequences begin to appear. So we start to see these marine sandstones, mudstones and carbonates appearing on a much larger scale. And so this is telling us that as we transition from the Archean into the Proterozoic, the amount of subduction is decreasing and the amount of stable continental margins are increasing. So we have no idea how many continents were present during the Archean. So through accretion and underplating, we know that the continental landmass that was around in the Archean was probably somewhere between 30 and 40% of the modern volume of continental crust. So that's by the end of the Archean, about 2.6, 2.5 billion years ago. So we know that we had less than half of the continental landmass that we have now by the end of the Archean. So these continents will have formed larger land masses, because every once in a while these small pieces of continental crust will have banged into each other to form larger pieces. And those larger pieces will have banged into other larger pieces to form really large pieces. So, that's the process of continental accretion. So although it's not 100% certain, it seems likely that there were two large land masses, or supercontinents, present in the mid to late Archean. Now these are called Valbara, which was between 3.1 and 2.8 billion years ago, and Cornerland, which assembled probably sometime around 2.7 billion years ago. Now please remember, these supercontinents would have been much, much smaller than other supercontinents that we're familiar with, like Pangaea. Okay, so just bear that in mind. We have much less continental crust, so they're going to be a lot smaller. But we do have some evidence for the collision between these continental land masses, and so that tells us, well, yes, they must have been crashing into each other, and so they must have been forming these larger pieces of continental crust. And when we time the collisions that we can find, we see they tend to occur in these two bursts, and that would suggest that you have lots of pieces of crust all bang into each other at approximately the same time, and obviously because they're all hitting each other at approximately the same time, they're going to all be suturing together to form one larger landmass. So we see the formation of these landmasses by looking at the orientation of metamorphic textures and the timing of metamorphism and crustal melting resulting from the collision, so we can see how and when the rocks are being affected by these two pieces of continental crust banging into each other. So a good example of this is we see deformation in rocks of the snowbird tectonic zones. This is in Canada. So it's on the northwestern coast of the Canadian Shield. And we see deformation between 3.2 and 2.6 billion years ago. And so what we see in this area is we see the area displays granulite facies. That's quite high temperature metamorphism, 700 to 1000 degrees Celsius. And that also means moderate to high pressure, and that suggests an orogenic event, a mountain building event. And so that would suggest between 3.2 and 2.6 billion years ago, this snowbird tectonic zone was a mountain range. And we see other examples of this. So we see examples from Archean rocks in Wyoming, Montana, and in the Mississippi River Basin, which also display deformation consistent with continental accretion. So this would suggest that, during periods of the Archean, we have all these small pieces of continental crust heading towards each other, crashing into each other, producing multiple small mountain ranges, suturing these pieces of crust together to form much larger land masses. So what about the Archean atmosphere? So the Earth's earliest atmosphere was composed of hydrogen and helium because that's what was in the circumstellar disk that the Earth formed from. Now this atmosphere would have been extremely tenuous and it wouldn't last long at all because the Earth doesn't have sufficient gravity to hold on to hydrogen and helium. They're too light, so as soon as the solar wind got strong enough, they would have been blown away. So the hydrogen helium atmosphere wouldn't have lasted for two reasons. Number one, the Earth does not have sufficient gravity. If the Earth wanted to be able to hold on to gases like hydrogen and helium, it would need to be about 16 times heavier. The other reason that we weren't able to hold on to this very early, very tenuous atmosphere is because we didn't have a magnetosphere. So you need a core to form a magnetosphere. which we didn't have for for the opening stages of Earth formation. And so without a magnetosphere, the planet or the proto-Earth would have had very little protection from the solar winds being given off by the young sun, and so these solar winds would have stripped away the early atmosphere very, very quickly. So just to give you some idea, here we have the planets. So we've got Mars. Where's Mercury? There's Mercury. Mercury, Mars, Venus, Earth, Neptune, Uranus, Saturn, and Jupiter. And these coloured bands here represent which gases the planets can hold in their atmosphere. So if we look Mercury, for instance, the gravity is so weak it can only hold on to xenon. It can't hold on to other gases like carbon dioxide, oxygen, nitrogen. Just doesn't have sufficient gravity. Mars does have sufficient gravity to hold on to carbon dioxide, oxygen, and nitrogen. However, poor old Mars has the problem that its core has completely solidified. And so that means its magnetosphere is rather weak, and so that means it doesn't have the best protection from the solar wind, and so the solar wind coming off the sun is constantly smashing into the Martian atmosphere, stripping it away. And so that's why Mars has this very, very thin, very, very tenuous atmosphere. Now, Earth and Venus, on the other hand, are both known for having quite good thick atmospheres. Gravity on both those planets is sufficient to hold on to xenon, carbon dioxide, oxygen, nitrogen, water vapor, ammonia, and methane. So, that's pretty much all the kinds of gases we have in our modern atmosphere. If you want to hold on to hydrogen and helium, on the other hand, you have to have a much higher mass, which we don't have. So once we have the protective magnetosphere, which is going to protect the Earth's atmosphere from the solar wind, we can begin to build up our atmosphere. So this atmosphere formed by a process of outgassing, and this is the release of gases from the Earth's interior via volcanoes. And so, the Earth's earliest atmosphere is going to consist of these volcanic gases. And so what we can do is we can go to modern volcanoes and we can measure the gases that come out of those and use it to approximate what the Earth's early atmosphere would have consisted of. And so we know the Earth's early atmosphere would have consisted of large quantities of water vapor, carbon dioxide, nitrogen, and a range of other compounds like sulfur dioxide, a bit of hydrogen sulfide, and a few other chemicals like hydrogen chloride and hydrogen fluoride. So yeah, the volcanic gases would be dominated by water, carbon dioxide, nitrogen, sulfur dioxide, hydrogen sulfide, carbon monoxide, sulfur gas, hydrogen, hydrogen chloride, and hydrogen fluoride. So a whole range of gases would have been released by the volcanoes. But water, carbon dioxide, and nitrogen would have been the main ones by far. The carbon dioxide and carbon monoxide and nitrogen would have reacted with hydrogen, which was being released by the volcanoes, and that would have led to the formation of methane and ammonia. Now, we know this early atmosphere has to be pretty oxygen poor, and we know this because when we look at clastic sedimentary rocks from the Archean, where they're where we have good enough rocks, we can see that some of the clasts in these sedimentary rocks contain pyrite and uraninite. So pyrite is iron sulfide and uraninite is uranium oxide. Now, these two minerals are not stable in the modern oxidizing environment. So if you were to take a piece of pyrite or uraninite and leave it outside now, they would very, very quickly break down because they would start reacting with the oxygen in the air. So the fact that these crystals could survive as clasts in sedimentary rocks and not break down tells us that the environment must have been very oxygen poor during these early stages. So the presence of these two minerals tell us that the Earth's early atmosphere had very little oxygen in it. We begin to see pyrite and uraninite disappearing from the rock record as we move from the Archean into the Proterozoic. And as we move into the Proterozoic, we start seeing the appearance of minerals like hematite, so iron oxide, and goethite, iron oxide hydroxide, becoming more common, which suggests that the amount of oxygen in the atmosphere is on the way up as we transition from the Archean into the Proterozoic. So the next point is, well, would there have been oxygen in the Archean? The answer is yes, there would have been. So obviously, where would it have come from? Well, we know that we can get oxygen in one of two main ways. The first way is through a process of photochemical dissociation. And that's when a water vapor molecule in the atmosphere gets hit by ultraviolet radiation from the sun. And this essentially blows up your water molecule, releasing the oxygen and the hydrogen which that water molecule is made from. And so obviously when you have two oxygens, they'll combine together and that will form a dioxide molecule. So this process accounts for about 2% of modern oxygen formation in the atmosphere. However, rates would have been a lot higher in the Archean because we didn't have an ozone layer during that point. So obviously the modern ozone layer helps to absorb a lot of the ultraviolet radiation coming from the sun. However, because we didn't have it, that would have meant a lot more ultraviolet radiation would have been striking the Earth's atmosphere during the Archean, and that would have helped to increase the amount of oxygen formation through photochemical dissociation. Now, the other method by which we can form oxygen in the Archean is photosynthesis. And we know that we have reasonable evidence for photosynthesizing organisms dating all the way back to 3.5 billion years. And so we know all the way back in the Archean there is good evidence to suggest yes, there were organisms around, they were photosynthesizing, and they would have been releasing oxygen as part of that process. The thing is though, is the oxygen would have been what we refer to as buffered. So as soon as the oxygen is produced, there would have been a chemical reaction that took place that would have more or less stripped that oxygen out of the atmosphere as soon as it was formed. And so this meant that during the Archean, because the oxygen was being created at quite a slow pace, it wasn't really a very fast process, essentially it means that any new oxygen that's produced is very quickly removed again. And so this means that you don't have the capacity to build up large quantities of oxygen in the atmosphere. It's not until the Proterozoic where we begin to see the amount of atmospheric oxygen really taking off. And this is because, and we see this in the form of banded iron formations, which are very hematite rich. So banded iron formations contain lots of iron oxide minerals. And so this is telling us that we have lots more atmospheric oxygen. We can also see at the same time, we also have a positive carbon-13 anomaly. And this is caused by carbon-12 entering organic matter, so plants in quite large quantities during the Proterozoic. So we see an increase in the amount of oxygen in the atmosphere, and a change in the carbon isotope ratio as we move from the Archean to the Proterozoic, and this is telling us that the amount of plant life in the Proterozoic got considerably larger. That helps to produce lots more oxygen, and so we can begin to build up a reserve of oxygen in the atmosphere. In the case of the Archean, because there's not much plant life, so photosynthesis is relatively, a relatively small contributor, and photochemical dissociation is also quite a small contributor of atmospheric oxygen. It means that the amount of oxygen in the Archean atmosphere is minimal to non-existent. And so this diagram just kind of summarizes the process of oxygen formation through photochemical dissociation and photosynthesis. Okay, so this third part has really gone on, for which I apologise. So good time to stop, get up, have a walk around, take 10 minutes, relax, take some time to, just get ready for the fourth part, and I'll see you in a bit.